go to design and quick layout. And that's my quick layout. It's my favorite one. You know, it's in the chart model, all this stuff. I think I'll show this again real quick. All these options, that's so many cool things. It's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey, how are we doing, everybody? It is time for office hours. We'll see if anyone's in the chat. We had someone on the Discord asking about office hours. So let's see who's here. Anyone here? Is anyone here today to do some work? I saw there was one person waiting earlier. Let's see. Where is everybody? Should go watch Mitch Flower Power. He's got 903 viewers. Let's see. I'll mute this. See if anyone joins in. We'll get some My Pearson up and going right here. Hey, what's up, Jesse? Hey, what's up, Ty? Make your chat bigger right there. Should we do some My Pearson? Chapter 12? Yeah, what do you want to do in chapter 12? Let me get the homework going right here. Okay. Edit. There we go. So many ads. Oh my gosh. The probabilities an adult man has high blood pressure or high cholesterol shown. Yeah, let's do that one. Okay. That was a little tricky. It's like conditional distributions. It's interesting how some of the topics converge. So we're getting the assignments open. The probabilities that an adult man. Okay. So we're going to be doing it about 313 Stat 201 chapter 12 quiz. The wording kind of threw me off. Yeah, it's a little tricky. You have to look at, like, given they have this, what's the probability of this? Definitely. Is it like not? Whoa. They're smart on their ads now. Trying to do something in the background there. They're like, no, you actually have to have the ad open. Wow, that's crazy. Interesting stuff. It's chapter 12 quiz, right? Chapter 12 quiz. Okay, here we go. There's so many on these. Let's go check it out. Oh, I found it right away. I knew it was towards the end, but I clicked on it right away. So here we are with the probability, and let me redo the timestamp here. The probability an adult man has high blood pressure and high cholesterol, and do take care of your LDL and HDL cholesterol. So fun stuff right here. Okay. So when we look at this right here, this is a proper probability distribution because either you have okay cholesterol or high cholesterol, or you have okay blood pressure or high blood pressure. So when you look at this right here, why is this a proper probability distribution? Hey, Colin, I ran my work. I know about our studio today. PS has, yeah, awesome. Such good news. Yeah, we've been talking about our studio, and we'll be communicating more on this and doing some cool stuff there with Stat 201 and everything. Thank you, Colin, right there. Let's throw out 100 points for Colin swinging by. A lot of our studio, everybody. That's really powerful stuff right there that a lot of companies are using these days. So why is this a proper probability distribution? Wish we could do this one in our studio. Why is this a proper probability distribution? There's two reasons. Like, why are the probabilities correct, and why is it a proper probability distribution right here? Like, what do you notice about each individual probability, and then what do you notice about all the probabilities? So the first rule of probabilities is that probabilities have to be between what and what? The first rule of probabilities is probabilities have to be between what and what? They add up to 1 is, yep, second rule right there, 100 points right there, Jesse, great job. And they're between 0 and 1. So this is a proper probability distribution. So if you want to look at the probability somebody has high blood pressure, it would be this right here. There is about 32% that have high blood pressure. It doesn't matter about the other one because that's the other variable right there, like what's the probability of this given this. But okay blood pressure would be right here, and we can go the other way going left or right. So to see the cholesterol right there. So let's look at what the question asks. It says to us, the probability that a man has both conditions. So to have both conditions, you'd have to have high blood pressure and high cholesterol. So what is the probability of high blood pressure and high cholesterol? Well, that's going to be right here in this cell right here, the 18%. There we go. The probability that a man has high blood pressure is, so we kind of just did that one. High blood pressure is just going to be this right here. So you could be in either of those groups. So what is the probability of having high blood pressure? what is the probability of having high blood pressure? So what would be the probability of having high blood pressure? 32%. I think the last two ones are a little bit more difficult. So I'm like, dun, 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 I can do it, my bet. The probability that a man with high blood pressure has high cholesterol. So now we need to look at only the men. So it says with high blood pressure has high cholesterol, right? Let's double check it. So man with high blood pressure has high cholesterol. So these are the individuals who have high blood pressure. And we want to look at if they have high blood pressure, what's the probability of high cholesterol? So think about this. There's a total of 32 down here. So how would you find out the probability of having high blood pressure if you have high cholesterol? What do you think we would do right here, Jesse? So what is the probability if you have high blood pressure that you would have high cholesterol? How would we do this? I don't know is a fine answer if you don't know. But I think they're kind of walking you through like kind of what you would do right here. As long as I did the which way is correct on this, we should be good. Oh, I don't know. Great answer right there, 100 points. So these are the individuals here who have what we're interested in. So it'd be... Does that make sense right there? So 0.18 out of the 0.32 meet the criteria. So you can see it's kind of more likely if you have high blood pressure that you'd also have high cholesterol. So we just divide the two numbers and that, yeah, once you see it, you're like, oh, that makes sense right there. So we're just going to divide those numbers. Is my mouse acting weird? I feel like my mouse acting odd today. Once you see it, it's like, okay, I get it. I get what's going on. I think it says don't do any round to 3 decimals, really. So we got to drop off 1 decimal. The probability that a man has high blood pressure if it is known that he has high cholesterol. So we're now switching it up right here to say it is known that they have high cholesterol. So there we go. It is. That should do it. Oh my gosh. Double check our answers. 100%. Great job, Jesse. Yeah, nice job. Quick on that answer right there. That's got it. Just adding up probabilities right there. Solving through the table. Looking at the percent of time this occurs out of the total time. So just working with some probabilities right there and saying like, oh, 18 or 0.18 out of the 0.43 have it. So that would be the probability given they have high cholesterol. I like to say given. So the wording of it can be weird. That's something we try to point out when we give tests is that we're not always going to use the same exact wording. So I think that's the tough part for people is like, there's nearly infinitely ways to word stuff. So you can't say, oh, we're going to word it this one way and you have to know it one way and then you can get it right. You have to be able to decipher a little bit where it says like, if it is known they have high cholesterol. So I like to say, given they have high cholesterol, what's the probability of high blood pressure? So we are just saying, okay, given high cholesterol, which means only this group right here, and then the probability of high blood pressure. So given high cholesterol, what's the probability of high blood pressure is the same thing as this question worded down here if it's known. The American Red Cross, you got it. Let's do that one next right here. The American Red Cross. Good job, Jesse. I like those, at least one. Here we go. Ooh, this is going to be a tougher one. It's going to be a longer one. The American Red Cross says. Okay, chapter 12, 933, Statute 1, chapter 12, quiz. The American Red Cross says. Okay, the American Red Cross says about 45% of people in the population have, U.S. population have type O blood, 39.7 have type A, type B is this, and the rest are AB. So what do you think we're going to do if we get information like this on the test? A lot of these problems focus around knowing what to do with the information. So what do you think we would do with this information right here? What do you think is the best thing we can do to help ourselves out if we get information like this? I'll be doing some chapter 12 right now. I'll feel free to mention a homework problem. It might also be on the quiz. Make a table exactly. So you want to make a table of the probabilities. That's going to help you out a lot. because then you're going to be able to look at them and add them up and see what's going on. So we usually write the event and the probability of the event right there. So we have 1, 2, 3, 4 types of blood, I believe. So 1, 2, 3, 4. And so we go here, the event O, A, B, and AB. And so O is 45, and oh, wait, that's right? And then A is 39.7. And then this, how are we going to get that last probability right there? How are we going to get that last probability? So this is one of the rules. It's kind of the complement rule, and it's also rule number 2. Rule number 2 is the probabilities add up to 1. We've written them here as percents. We could write them as decimals too if we want, but we could put a little like percent right here so we know this is all in percentages. Just to remind us, we're not doing decimals in this moment, which we could have done if we wanted. But we're missing a probability for AB. How are we going to get that? Exactly. We can subtract from 1. So we're going to go here to 100. We can do 100 if we want. Just if we're doing decimals, it all depends. Minus 45, minus 39.7, minus 11.2. There's the 4.1. Now to check your work, I would make sure it all adds up to 100%. So you can take all these numbers and add them up, but it looks like it does. Yeah, I'm pretty sure it does. We should be good. Cross your fingers. And with that right there, we have the table. So now this problem becomes a lot easier. I'm going to put them side by side because with this table, we really help ourselves out. And I think that's where just taking a little bit of time to write out your problem is going to make your life a lot easier. So that's what we want. We want to be on easy street for a lot of these problems where we have the information right there, easily presentable to us, and now we can get the problem right. The probability that someone has AB blood, they start out right there with the missing one, and they want it to 3 decimals, so they want it as a proportion right there. They're not doing it as, they are doing it as decimals, I believe, because it says report to 3 decimals, and we're doing it this way right here. Be very careful. I'm 99% certain. If for some reason you got it wrong because you entered everything in the other way, let me know. I'll fix it up. How are we going to get the probability someone has type A or B blood? Now, you can't have A and B blood at the same time, meaning these two events are disjoint because you can't have type A blood and also have type B blood. You can have type AB blood, but that's not A and B blood. That's AB blood. It's not you have A and you have B, you have AB. So how are we going to get the possibility of A or B? Nice and easy with what we have right here. What can we do to get the probability of A or B blood? How are we going to get the probability of A or B blood? Because they are disjoint. And if they are disjoint, we can simply what them. There's a key thing. Mutually exclusive disjoint events can easily be whatted together. And there we go. Jesse has it right there. We're just going to add them together. That's exactly it. And make sure you know the rule. This is a key thing to write down right now. That if things are disjoint, meaning if one happens, the other can't, you can simply add them together. So we're going to do them as a decimal right there. And there we go. Boom. The probability the donor is not type O. So this is the complement. Great job, Jesse, right there. Nice and easy because we can see the probability is 45%. Someone is either O or not type O. You could add up the bottom ones right there, but it's just going to add up to 55% because someone is either O or not type O. To get the complement, simply take and subtract from 100 or 0.1 or 1. And great job, Jesse, following along. Yep. Now, this is where it turns into multiplication problems because we're talking about multiple donors in a row. And what would you say about if someone walks into the clinic to donate blood and another person walks in? The next person walking in, their blood type would be what of the previous person? So what would you say about that? Think about words you would use. Are they disjoint? Are they mutually exclusive? Are they dependent? Are they independent? The person who walks in to donate blood next would probably be what of the person who is giving blood currently? So we have 4 potential donors, and the person who walks in next would probably be what? They'd be independent. And that means they don't influence the blood type of the other person. Be very careful with these words. Know them really well. That disjoint means if one thing happens, the other thing can't. And independent means that if one thing happens, it does not influence the probability of the next thing occurring. So knowing the words very well and understanding how to apply them to scenarios like one donor walks in, the next donor walks in, their blood type would be independent of the other person. A person's blood type is disjoint here that they can't be A and B at the same time, meaning if they are type A blood, they can't also be type B blood, meaning we can add together the probabilities. The importance here with the disjoint down here, the independent right here on these is that when we do independent, we can multiply probabilities together. So we have the probability that people are all type O blood. So to be all type O blood, the first person would be O, and then the second person would be O, and then the third person would be O, and then the fourth person would be O. So what is the probability here, Jesse, of the first person is O, and the second person is O, and the third, and the fourth? And is the key word, because when we say and, we are just multiplying probabilities. So what would be the probability that they're all type O blood? The first is type O, and the second is type O, and the third is type O. What would be the probability of that? These are really great problems right here. Like this goes over the multiplication. It might be that. Let me check. 2, 3, 4. There we go. You got it right, Jesse. See, Jesse, great job, Jesse. There we go. There's the probability right there. The probability that no one is type AB. So the first person who walks in the clinic, what is the probability they are not AB? Just focus on that. The first person who walks in the clinic, the probability they are not AB. Just the first person. Only focus on the first person right now. So don't worry about all four. The first person, boom. And the way we're finding that is you're either type AB or you're not type AB. So that's the complement. So what would be the probability the first person's not AB, and the second person's not AB, and the third person's not AB, and the fourth person's not AB? And if you're hopefully following along, you'll see I'm saying and all we're going to do is multiply those probabilities. So the first is not, and the second, and the third, and the fourth. It might be that. And that should just be this to the fourth power, which is the same as multiplying it 4 times. So to get not type AB, we're going to take and do the complement. There's not AB. Second person, third person, fourth person, and there's the probability. So great job, Jesse. Yep, that's got it. The probability that they are all not all type A. Okay. Whew. I gotta decipher this one. So where it gets a little tricky. I do remember the last 2 ones here are a little complicated to understand. They're not all type A. Okay, so either they're all type A or they're not all type A. Let's expand this. To solve this one, we need the complement, because one of these things must be true. All type A or not all type A. So imagine you have 4 people walk into the clinic. And only think about the first scenario right here. You have 4 people walk into the clinic. Under the first scenario, it is possible that all 4 of these people what? Boop, boop, boop. You have 4 people walk in. Under the first scenario right here, Jamarcus, you got it. We'll do that in one next. Under the first scenario, it is possible that what? So just think about that first scenario right there. Under that first scenario, it is possible that all 4 people would what? They're all type A. So that is possible, right? It is possible that they could all be type A. But then the only other alternative is that they're not all type A. Either all of them will be type A or not all of them will be type A. So what is the probability all of them are type A? And these are like the problems we just did a second ago. What is the probability that every single one of them is type A? One of these things must occur because they're complements. The best way to understand that they're complements is that we use the not word right here, because either this occurs or it does not occur. That's the best way to like say things like at least one, and that might be the answer right there, Jesse. Great work. So all 4 are type A, which is going to be 0.397 to the 4th power. So with this right here, let's solve that. 2, 3, 4. There it is right there. Great job, Jesse. And what we get when we solve this, and we're going to carry some decimals here on this, is, well, that might be enough. When we solve this out, I think that's enough, right, Jesse? Because it only wants 3 decimals. Go away. We're going to algebra this now. And when we algebra it, we bring this over to the other side right here, and we do 1 minus. And now we get the probability right here of not all type A is equal to this right here. because, and especially once you go through and double check your math, you can see that this would equal this right here. And great job, because it has to be the probability that they're all type A is this is 0.025. And then the probability of that not occurring would be the complement, because either that occurs or it does not occur. So these are trickier problems. The more you get used to them, the better. I think we've carried enough decimals. Let's double check right here. This should round. Yep, there it is right there. We did it. And the probability that at least one person is type B blood. So this is very similar right here. At least one person is type B blood. So either what? Can you write out this sentence, Jesse? This is a good test of your knowledge right here. Write out the sentence that something, 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 or something, something, or we could say at least. So what would be the thing that we can solve for that will help us solve this? This is where usually people get stuck. So I'm looking for this. So either this or at least one person is type B blood. So we need the thing in bold right there to solve, because then we'll just do the same sort of trick we just did a moment ago. So what is that thing we need to do right there? It's all right to say I don't know, but at least close. So think, well, so either at least one person is type B blood, because it could be one person has type B, two people have type B, and that's what we're looking for. At least one person has type B, right? The probability that at least one person is type B. Okay. So either, because think about this. You could have the case, you got 4 people here, right? So if at least one person is type B, it could be one person, 2 people, 3, or 4 people. If at least one person has type B blood, it could be one person, 2, or 3, or 4. So what's the other scenario we have not included in this? If at least one person has type B blood, then it could be that one person has it, 2, 3, 4. The only thing we haven't included in here, which would be the set of everything that could occur, would be what? You're really close. And you're kind of on the right track with your first answer. But this is the key to solving them. Has to include everything. That's what 1 means, is everything's been thought of. Because we're saying this is everything that could occur. It also is disjoint because either this or this occurs. So what's the complement of at least one person is type B? Here, I'll put, you ready? Watch this. Let's rewrite this. Instead of at least one has type B, someone is type B. How about that? That makes it easier to understand the complement now. Because if I say at least one person has type B, someone is type B. At least someone is type B. There's someone with type B. Like it could be 1, 2, 3, or 4 people, but someone has type B. I think you'll be able to figure out the complement with that. Because at least one means there's someone who has type B blood. We're looking for someone with type B blood. If we have at least one, we're good. So someone has type B blood. What's the complement of somebody having type B blood? For this group of 4 people, either someone has type B blood or what? And I think that'll make more sense. If you say it's either the case that someone has type B blood or what? I think you got this, Jesse. For 100 points. And out. Pretty much, well, not that someone doesn't have it. It's not either someone has or someone doesn't have it. Put the not earlier on. You're right there. I'm throwing another 100 points. You're right there. Because it's either the case that somebody, like one person has it, 2, 3, 4. When someone has it, it's at least one person has it. So it's either the case someone has type B blood, or think of you're right there. Because if one person has it, then there's also the case that someone doesn't have type B blood. But we want to say either somebody has type B blood for these people or no. It's either the case that someone has type B blood or what? You're right there. You got this. It's either the case that someone, because this is the big hurdle to get over, to be like, okay, either someone has type B blood for these people, which could mean one person has it, 2 people have it, 3 or 4, or it's the case that nobody has it. Exactly. Okay. So now we've got it. Great job, Jesse, right there. It's either the case that no one has type B blood or someone has type B blood. So what's the probability of nobody having type B blood? I think you can get down pretty quickly, because think the first person doesn't have type B blood. The second person doesn't have type B blood. What is the probability of that? I'll even give you a hint right here. The first person not having type B blood is that. So what's the probability of nobody having type B blood? So it'd be the first person doesn't have type B blood, and the second person, and the third, and the fourth person don't have type B blood. So what would it be? Probability of nobody having type B blood. First person doesn't have it. Second and third and fourth person don't have it. That might be right. Let's take a look. Great job, Jesse. And boom. There you go. Double check. Let's double check our math here, Jesse. Did you double check your math? Did everything work correctly right here? Let me double check. 0.88. 2. Whoops. 2, 3, 4. That's what we should get right there. Double. Oh, no worries. 100 points again. Don't worry. Good practice. So all we're going to do is the same trick here again. And we're just going to go right here and subtract this off. These are some of the hardest problems for people. Some people get to the test questions on these and say, I got no idea. They say, what are we trying to solve for? And I say, complement. So, and there's the steps. The writing of the sentence is often the hardest part. 378. We should be right. Let's find out. If I do that, we'll get it wrong. Yay! There we go. Great job, Jesse. Is it making more sense, Jesse? It's a lot of these come down to, write out the distribution, understand what disjoint is, understand what independent is, and then also the complement questions are some of the toughest because you often have to write that sentence to be like, okay, either nobody has type B blood or somebody has type B blood. And then the nobody has type B blood is going to be the easier one to find because the probability of the first person not having it, second person, third person, fourth person is 0.88 to the fourth power. If we write this out in more of a traditional fashion, it's going to look like 0.88 because the first doesn't have it, and second, and third, and the fourth. So it's going to look more like that to say the first was not type B, and the second was not type B, and the third and the fourth were not type B. And then we can just solve this and then reduce and find the answer over here. So pretty tricky questions, really good stuff right there. And Jamarcus has one, the 2015 study. Let's go find that. We did mark this question, right? Boop. Wait, solve that one, right? We did the Mars one yesterday. I think it's also the quiz. A 2015 study. A nervous kicker. That's a tougher one. It's got a little trick to it. Oh, there it is. Oh, we got 2 of these. Okay, a 2015 study. 2 of these to do. Here we go. Let's mark them. 2015 study. Stat Tool 1. Chapter. Okay, here we go, Jamarcus. So check it out. Feel free to answer along. We'll practice. More. Tell me more. Good. Okay, let's check it out. So this right here is giving you different probabilities, and you have to be careful. You have to think about how the rules apply. A 2015 study found that 51% of households had no landline service. Okay. So the probability of having landlines, let's put this in a table. Always good to take the information and kind of draw it out. So we need a table over here. And the table is going to have the event of landline. So event, probability event, and landline, no landline. And not having a landline is 51%. Landline is 49%. Okay. This raises concerns about the accuracy of certain services as they depend on random digital dialing. Researchers pick 3 households. Okay. So what is the probability that all 3 of them have landlines? So the first has a landline, the second has a landline, the third and the fourth have landlines. So what is the probability that all 5 have landlines? So it's 5 households, right? So 5 households have landlines. 5 random households have landlines. 5 random households have. What is the probability of this right here? Bowler, you got it. We'll do it here next. Jesse, you got it. So what's the probability all 5 have landlines? This is going to go to some really good review of what we just did too. So the first has a landline and the second. First has and second has ... and fifth has. What is the probability of this? They all have a landline. The first has a landline, the second has a landline, the third has a landline. I don't even know what I'm capitalizing anymore. Might be. Because this is 0.049 times 0.049. And just repeat the process. I guess we could write it out right here. 0.049 times 0.049 times 0.049. And that's 0.049 to the 5th power. And let's go right here. 0.049 times 2, 3, 4, 5. And there it is. Oh, we got different answers, Jesse. Let me double check my work. That's why I love having students here. And thank you, Jesse. Another 100 points. I do make errors. 2, 3, 4, 5. That's what I'm getting, Jesse. You might have a different version. But the probability that all 3 of them... Oh, no, it says 3. Well, since it says 3, that just means we go right here and do the following. So even I read the question wrong. Oh, you put in that? No worries. Well, I read the question wrong, too. It's 3 houses, so 2, 3. Just have to change the amount of times we multiply it together to get the, and third has. Well, the and's probably more important than the has. I don't know. I don't know what we're doing. Because the and is the multiply. So when we say the first has and the second has and the third has, why do you multiply all them? Because this is the probability of things occurring at the same time. Each household is independent. We assume it's random houses, as they say. So when we have random things, we can look at the probability of things occurring at the same time. And next one is yeah, Ethan on the right track. So we're going to go with it, right? Does that make sense, Jamarcus? Because when you say this occurs and this occurs, the probability of things occurring at the same time is the multiplication rule. So, but if we are looking at 2 things, like what's the probability of a random Stat 1 student winning a prize, 1 in 100 chance, and you have a wheel. You ever see those big wheels that you spin and you go up and you go... So you walk up to this big wheel on campus and it's got like free Chick-fil-A and it's a 1 in 100 chance of winning it. And I'm not saying you spin it with, you just spin it, you go woo, and that thing goes crazy. So what's the probability that you and your friend win free Chick-fil-A? What's the probability that you and your friend win free Chick-fil-A? So you're going to spin it and then your friend's going to spin it. So what's the probability that you and your friend win free Chick-fil-A? This is the same sort of idea for this previous problem. So you might win free Chick-fil-A. Would that make your friend more likely to win? No, it's the wheel's going to randomize. I mean, we're not saying... I mean, you could say, what if we figure out a way to spin it? We won't go into that sort of depth with the problem, but we're just saying you spin the wheel randomly. Your friend spins the wheel randomly. You each have a 1 in 100 chance of winning free Chick-fil-A. What's the probability that both you and your friend win free Chick-fil-A? So the probability of free Chick-fil-A is 1 in 100. I obviously want Chick-fil-A today. Want more coffee. So what's the probability of winning free Chick-fil-A twice? So you win Chick-fil-A. Careful, Jesse. That is the probability of winning free Chick-fil-A or winning free Chick-fil-A as though there's 2 spots. So that would be the probability. I think it has to do what you did. If you did this, this is the addition rule. The addition rule is when we add probabilities, i.e. the addition rule. And this would be phrased, you win free Chick-fil-A or you win free Chick-fil-A. Now, the key words right here, and this is to review the chapter, is or. And then we have the multiplication rule where we multiply. And what's the key word for the multiplication rule? What's the key word for the multiplication rule? Great job, Jesse, right there. Yep. What's the key word for the multiplication rule? And then there is a rule for these. And the rule here is disjoint. We'll talk about that in a second. And the rule here is independent. So here's two types of problems and the solutions. So this is the Chick-fil-A right here. And then there might also be McDonald's or something, or we'll put the same probability. So there's 2 free meals on the wheel. The probability of Chick-fil-A is 1 out of 100, and the probability of McDonald's is 1 out of 100. What's the probability that you win free Chick-fil-A or McDonald's? So when you spin this wheel, what's the probability that you win free Chick-fil-A or McDonald's? There's 100 spots on the wheel. There's 2 free meals, and you could win Chick-fil-A or McDonald's by spinning the wheel. So what would be the probability you win Chick-fil-A or McDonald's? What would be the probability of winning Chick-fil-A or McDonald's? Correct. Now, why are they disjoint? What does it mean that they are disjoint? When you spin this wheel, they are disjoint, and explain to me why they are disjoint. Like, use the concept of disjoint, which means 2 things cannot occur at the same time. When you spin the wheel, if you've ever spun one of these wheels, why is winning Chick-fil-A or McDonald's disjoint for somebody who spins the wheel? And what do you mean? Keep going, Jamarcus. I think you get it right there. They're disjoint because when you spin the wheel, winning Chick-fil-A or McDonald's, well, if one happens, the other can't, right? For you, and we're just talking about for you, the probability of you winning Chick-fil-A or McDonald's, you either win Chick-fil-A or McDonald's. Both could not happen, but they both can't happen at the same time. Like when this wheel spins, it can't land on Chick-fil-A and McDonald's at the same time. So actually the probability of Chick-fil-A and McDonald's is 0 because they both can't occur at the same time. Disjoint events, if one occurs, the other can't occur. They're very dependent. We don't like to often blend the terms, but it is true that disjoint are dependent because winning Chick-fil-A would depend on if you won McDonald's. Like if someone says, I won McDonald's, I know they didn't win Chick-fil-A because you can't have them both occur. Now, this one right here, the independent with the and goes to 2 people playing the wheel. Now, 2 people are going to spin the wheel. And what is the probability of both of them winning McDonald's? Well, it's the first person wins McDonald's and the second person wins McDonald's. But let's change it up. What is the probability that both people win a free meal? So think about this. Probability, both people win a free meal. What is the probability both people here win a free meal? And they could win any free meal. Well, it depends on the question, Jamarcus. We'll see a lot of different questions and knowing what to solve and when. And writing a sentence is very important. So here, I'll write the sentence for you how I would solve this. First person wins Chick or McDonald's, and second person wins Chick or McDonald's. So here is the sentence. This is the sentence you need to solve for. So what would be the probability of the first person winning Chick or McDonald's and the second person wins Chick or McDonald's? And I think I know it. So can you solve this out right here? The first person wins Chick-fil-A or McDonald's and the second person wins Chick-fil-A or McDonald's. Jesse has it right there. Exactly. Because the probability of someone winning Chick-fil-A or McDonald's is simply going to be the addition of both of these. And then the and is the multiply right here. And the second person is the same sort of mathematics on them winning some sort of free meal. So you can see where we have the addition right here. I'll underline that. And so we underline these and then we bold this to kind of draw the connections between the or being the addition. So the first person wins Chick-fil-A or McDonald's. Those are disjoint, so we can add them. And then the second person, which we're going to multiply. And why can we multiply these? Because what the first person does will what? Why can we multiply these? What the first person does on the wheel and the second person does is what? Why can we multiply these probabilities? What the first person does and the second person does on the wheel, exactly, they do not affect each other. So if the first person wins something, it's not going to influence the second person. We could come up with some crazy scenarios, but that's what independent means, is that whatever I get on the wheel is not really going to impact what my friend gets on the wheel because we're going to spin it. It's going to go, those things are really very light. So you spin it and it spins like crazy. So, and if we give it a little spin, they're going to be like, spin it again. So we just did this one right here. The probability they all have landlines is 0.04923. There we go. And round of 5. Oh my gosh. What is the probability that at least one of them does not have a landline? Okay, so this is where we have to write a sentence. What is probability at least one does not have a landline? So it will be the case that at least one does not have. What's the other case right here? And here's the or, which is going to be our addition. Something, something. What's the phrase I'm missing here? And these are the toughest parts. So at least one does not have a landline. So it'll either be the case that at least one does not have a landline or what? Exactly. Or they'll all have it. So either all have landlines or at least one does not have a landline. So let's go ahead and algebra this out to kind of solve for what we want. The or becomes a plus because these are disjoint events. We can just go here and add this to the other side. And this would be subtracted because you have to subtract. It's how algebra works. To bring something positive, because this is kind of like a plus over here, you would have to subtract it off of both sides, and you get the algebra equation right there. So what's the probability all the houses have landlines? What's the probability every house has a landline? And what's really great is I think we just solved for that. Here's the probability all the houses have landlines. So we're just doing 1 minus that. And there it is right there. There's the probability of at least one not having a landline. Because either they all have landlines or at least one does not have a landline. What is the probability that at least one of them does have a landline? So this is a little bit of a trick right here where they're reversing it. So now, something, something. Or, was it at least one doesn't? At least one of them does have a landline. Okay. At least one has a landline. So at least one house has a landline or what? So you've got 3 houses, and at least one of them has a landline. So it could be that one has it, 2 or 3 houses have landlines or what? At least one house has a landline or what? What's the other case we haven't considered? It's the case that at least one has a landline or what? Boom, Jesse, you're getting it. You're on track with these. This is where the practice comes into play. None have a landline. Is it making more sense, Jesse, to like write these out? Then once we have this written out right here, we're simply going to take it and put in our addition right here. Yeah, this is the practice. And when you get to the test, you're like, okay, I've done a lot of these. I know what I'm looking for. I got to write my sentence, make sure my sentence makes sense. And then I'm just going to solve for the probability none have landlines. And the probability none have landlines is going to be the first doesn't have a landline, the second and the third don't have landlines. So we're just going to multiply. Oh, yeah. You just have to, you have to get it used to doing it and understand the multiplication rules, the complement. I definitely support writing them out. It's the best way to understand, do these problems, and then you can usually get them correct. So it's practice makes perfect, really, with these problems. These are the toughest problems. There's not a ton of them on the test, but a lot of people get stumped by these and they say, I got no idea. They just look and they go, what in the world? How do I do that problem? So a survey of National Health found 71% of adults have a cell phone and no landline. I think it only talks about that then. This raises concern about the accuracy of certain surveys as they depend on a landline. So what's the probability that these adults only have a cell phone and no landline? So, hey, Brian. Hey, Philip. Great job right there. 100 for passing your physics exam. That's a tough exam. That all of these adults, how many adults are we talking about? 6. So with this question, it's very similar. I might do this one a little bit quickly, and then we'll do Jesse's question, because this is the same sort of problem. And we're saying that they have only a cell phone. See, it says right here, only have a cell phone, only have a cell phone. So you really only have to focus on only have a cell phone, because they really just add on this no landline right there. And I think Jesse's already solving these because the 71% is the percent that have only a cell phone. So we're talking about how many adults again here? How many adults? 6, right? Where is it? 6. There it is right there. So 2, 3, 4, 5, 6. There it is right there. Great job, Jesse. Round to 5 digits. Okay, so that's the first one. What is the probability that none of these adults have only a cell phone and no landline? So none of them. So we would have to say it's not the case that it is true. So this would be, that's the case that they don't have only a cell phone. And so it's 6, right? 2, 3, 4, 5, 6. And that's why they have you carry all the decimals. So 1, 2, 3, 4, 5. Right there. What is the probability that at least one of these adults has only a cell phone and no landline? So it's, I think they're just reversing this one right now, that at least one of these adults has only a cell phone because either none of them have it or at least one has it. That should be right there. There we go. So once again, and great job, Jesse, definitely following along. And then, yeah, last decimal place right there, it looks like. But these are pretty exact on the answers. But if you look at how we did the last problem, we did the last problem a lot slower and wrote out all our work here and followed through all the mathematics. And if you look at the speed at which we can do these problems with a good bit of practice, it becomes a lot quicker. So I think that's the tough part for these problems. So I wanted to do the second one, which is basically the same sort of question, doing the complement, understanding what the questions mean. It's all about writing these sentences right here. So you basically have another version of the problem right here when you do this. And so definitely check those out. Jesse had another one. Which one did you have, Jesse? You had... Which one? We did Jamarcus's question. A certain bowler. There we go. A certain bowler. Yep. Thank you, Jesse. And we need more questions after this. A certain bowler. Oh, there it is. I skipped one and then we did it right here. Okay. A certain bowler. A certain bowler. Okay, a certain bowler can bowl a strike 90% of the time. Oh my gosh. That's pretty good. You'd be amazed how hard it is to get a perfect game, though. Okay. A little tricky right here. We'll write out each of these. Okay. So we have a certain bowler can bowl a strike 90% of the time. So we basically have a very easy probability distribution right here, where 90% of the time they get a strike. And so we have strike or no strike. And we have the event of strike and no strike. And the probability of an event is 90%. I used to not write these things out, but then I've noticed it makes things way easier. So the more you write these out, the more you practice them, you get ready for the test, and then you have your strategy for the test. And you're like, okay, I write it out. I see what I got right here. So what's the probability she goes 3 frames without a strike? Pretty easy to calculate. So she doesn't get a strike, she doesn't get a strike, and she doesn't get a strike. Now, the problem is we have to assume there's independence right here, which is a big assumption because we're about to multiply things together. So it should say assume independence for all these. Because it's like you get hot or cold in sports. So it's like, maybe she's like cold or hot or, you know, like on a streak or not on a streak. So what is the probability she doesn't get a strike and doesn't get a strike and doesn't get a strike? So what would that be? I think that is correct, Jesse, because it'd be no strike times no strike times no strike. And be there. Because we're assuming independence, once again, with sports. I should wear my sports shirt today. You might not be right to assume independence. And there we go. The probability of her making her first strike in the 3rd frame is this. Okay. So when you think about her making her first strike in her 3rd frame, the way bowling works is you get multiple frames. So it would have to go like this. Not a strike here, not a strike, and then a strike. So what is the probability of this occurring? That she doesn't get a strike, doesn't get a strike, and then gets a strike. So I think I can do it. Yeah, I think I can. I think I can. It's going to be very similar to the last one, but the last digit's going to be different. So she doesn't get a strike, and she doesn't get a strike, and then she gets a strike. What's the probability of that? So no strike and no strike and strike. You got this. And I don't know is always a fine answer. What is the probability? I think you got this, though. Yep. Last number's different. Oh, I already moved the decimal. There we go. There it is. Her has at least one strike in her first three frames. Okay, so this is pretty easy. So think about this. She either gets no... Well, I don't want to say... I'm about to do the same thing, and I basically said the answer. So I want to... This is the practice once again. We always try to do practice to make sure you can get it. So at least one strike or what? And we have to put something, something. Or this. So what do we have right here? She gets at least one strike or what? So what do we have right here? She's either going to get at least one strike in her first three frames or what? She'll either get at least one strike in her first 3 frames or what? No strikes. Exactly. See, then you start to be like, oh yeah, she'll either get at least one or she won't get any strikes. So no strikes or at least one or at least one. And one of those things must occur right there. And so now we just take this, edit over to their side. And now we just solve for no strikes, which we already found in a previous problem. No strikes is point... Yeah, Jesse, I think that's it. Because we already found that, right? Was it that? And then the answer is going to be... Because we already have it over here on the other screen. But that should be it. Great job. There's that up there, and it's just 1 minus, because either she'll get... And it was talking about a random 3 frames, but the first 3 frames is the same deal as a random 3 frames. The probability of a perfect game... So there's 12, and I think they added this recently. I think they added 12 strikes. A lot of people forget that on your last frame of bowling, the 10th frame, you get the last 2 right there to round it out to get all 3 strikes. So you have to get 12 strikes in a row. So what's the probability of getting 12 strikes in a row? Not that hard to calculate. So even if you're a 90% probability bowler, what's the probability of getting a strike? I'll strike, and then strike, and then strike, and then strike. It might be, which, man, if that was... It's a lot higher than I thought. So it would continue out there, and that's 0.9 raised to the 12th power. Surprised it's not lower than that. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What's 0.9 to the 12th power?
It's approximately 0.2824.
There we go. Double check your work. Especially if you're hitting repeat that many times. Always good to make sure you have it. Round to the near 1,000th digit. So the thousandths is right here. Remember, tens, hundredths, thousandths, 10,000ths right there. And yeah, so is there any? If you're wondering why it's tenths, it's because if you have your, you'll probably know this, but if you put right there the 0.1, it takes 10 of those to make a 1. If you put your 0.1, those are hundredths because it takes 100 of them. Like a penny is 100th of a dollar. That's why it's called hundredths. It probably knew that. I think we have everything rounded correctly. Thousands. Check answer. We got it correct. There we go. Yeah, that's got it. Good work. Good question, Jesse. Really great questions. What else are you wondering today, Jesse? We've done a good bit of these. Maybe we'll do one of the light bulb problems. Those are usually pretty tricky for people, but we've actually been doing them right now by doing these. We've done some of the hardest problems on this, but drop more questions in here. Thought we had some more people going to swing by. Maybe we will. Maybe we'll do the light bulb one or the soda bottle one. Once you know how to do these, they're usually kind of pretty quick. Google Drive signing me out right there. A rolling doubles on Paradise. Like, yeah, let's do one next. Here, watch this, Jesse. You ready? If you buy something, what's the probability you win something? It's the probability they're not all losers. 6-pack. So, winning symbol, yeah. 2, 3, 4, 5, 6. There we go. The work, what is the probability at least one is defective? The probability, so they all work, or at least one's defective. How many are we buying? 5-pack, 2, 3, 4, 5. It's gonna round. Man, look at that round on that. There we go. There's those. Yeah, someone doesn't like to watch basketball. After rolling doubles on a Paradise. Let's go to that one. once you know how to solve the problems, they usually are pretty quick. I love this chapter. I love probabilities. So after rolling doubles. After rolling doubles, here we go. Let's go look at this one. This sounds to me like some sort of independent thing because after rolling doubles, it's not really awesome. Jesse, I'll do these ones in the video. Thank you so much for being here. Both of these will be in the video for you to check out later. But yeah, so check them out. And Jesse, thank you so much. Another 100 points for being here. Really appreciate your questions. If you have more questions, you can always ask them at any time. So we're going to drop these other 2 questions in here for Jesse and check them out later. I've got them marked in the video for you. So after rolling doubles on a pair of dice 3 times in a row, your friend exclaims, "I cannot get doubles 4 times in a row." That's the, thank you so much, Jesse. I appreciate that. That is literally gambler's fallacies, we sometimes call it, or people, what am I thinking of? Not law of large numbers or law of averages. Law of averages says you're bound to average out. If you roll doubles a whole bunch, you're probably not going to roll it again. But these are completely independent. So your probability of rolling doubles on a pair of dice is always 1 out of 6. So they actually have a pretty good chance of rolling doubles again. The previous 3 times, because they've rolled it 3 times in a row, are not going to influence. It'd actually be 1 in 216, I believe, if I know my 1/6 properly. So because 1/6, 1 in 6, 1 in 36, 1 in 216. But then the next time is not influenced by the previous 3 times that just occurred. You might say, well, what isn't it multiplied by 6 again to say, oh, this is virtually impossible? But those 3 times have already occurred in the past. So the 4th trial is independent of the previous 3 trials that just occurred. And that's what this problem is going to get at with the answer right here. Explain why this thinking is incorrect right here. With so many, nope. There's no law of averages. So your friend is saying, I'll average out. I'm due to like not roll doubles. The 3 dice rolls do not affect the 4th dice roll. That's it right there. Law of averages is the fallacy. That is when people think that I've won or I've lost, and that's going to influence the probability of me winning or losing in the future, especially at games of chance. Also sometimes called gambler's fallacy. Tyler, good to see you here, and feel free to ask some more questions. We only have 1 more question, so we need some more questions, or I might start doing some, R Studio. But you never know. R Studio is a lot of fun. And Jesse had 1 more right here. Jesse said, if someone doesn't like to watch basketball, oh no. If someone doesn't like to watch basketball, let's get that question going. We have time for a lot more. If someone doesn't like to watch. Okay. Someone doesn't. Let's go check that out. If someone doesn't like to watch basketball like me. Hey, Meath, good to see you here. Oh, thank you so much, Meath. Yeah. How's your semester going, Meath? Throw 100 points. Hey, Cassidy, good to see you here too. Ask questions. We've been doing a lot this morning, so let me know your questions. We're just working away right here. We've got here, someone doesn't like to watch basketball. What is the probability that she will be a football fan? Okay. It's very similar to one of the earlier problems we did where it had high blood pressure and high cholesterol. So let's go check this out. So if somebody doesn't like to watch basketball, they'd be part of this group right here, which is 66% or 66 individuals. So what's the probability they're not a football fan? Maybe it should just be this. There we go. 30 out of 66. This is a conditional probability right here, so 0.4545. Interesting. Rounds up, right? Oh no! Let me double check it. If someone doesn't like to watch basketball, what's the probability? Oh, I did. It should be 36 out of 66. Which is, yeah, I should have done that. What am I doing wrong? What am I doing wrong? Yo, I worked the problem. We got no problems wrong today, and then all of a sudden now we're just going crazy. Okay. This. If someone doesn't like to watch basketball, if someone doesn't like to watch basketball, the probability that she will be a football fan is this. 36 out of 66, right? 36 out of 66. Whoops. I'm just gonna keep doing craziness right here. Let's just keep missing the problem there. There we go. Taking 340 with Professor Quick. Awesome. Charlie Quick is awesome right there. great friend of mine, really great colleague, and that's an awesome class. He'll probably know how to solve these problems better than me and not make simple math errors. The first time we did it, we solved it the wrong way. We said, if somebody doesn't like to watch basketball, what is probably they don't like to watch football? We did the not like to watch football. And the second time we did it, we just didn't know how to write decimals because 36 divided by 66 is 0.545, not 0.555. So just can't carry those decimals at the end right there. Trying to get it correct. But yeah, an employee of the month, Meath. That's awesome. We have a lot of students who are really trying to rack up those points and definitely earning a lot this semester. Trying to think what else there is. We might do a little R. Let's see. Preview of today's class maybe for 320. Well, let's get R going over here. Let's talk about. But if you have 201 questions, let me know. Or if you're here for 320, let me know. Let me mark the video. Marking the video. 10203 BS 320 preview of week assignment. Okay. So this week we're kind of doing some theoretical stuff, so to say, or some concepts that kind of talk about issues or problems we might have with the regression. So we're kind of judging our regression and thinking if it's a good idea. So it's very much, are we doing the right sort of ideas with regression? So there's a lot of codes we can run right here. We'll try and make these graphics look a little bit nicer maybe. Once again, we're always looking for good screenshots. We want our reports to look excellent, stunning, that we hand in a report and someone's like, whoa, where'd you make this? And you're like, oh, it's our studio. And they're like, no way, I didn't think programming could look this good. You're like, yeah, you can do anything. Anything is possible. So we're going to make a simple regression right here and talk about some of the concepts. This is the MT-CARS data set. And once again, this is just showing the concepts of what we're doing as though we can visualize a model here really quickly. And we just use some of the base codes or the reg class codes to get regressions done. This also applies to 201 because we are doing a regression right here. And we can easily summarize this regression to get the slope, the intercept, the R-squared adjusted, which we'll start interpreting that. The root mean square error, which is the typical miss the model makes, and all these things can be interpreted, but we're not focusing so much on that this week. We're focusing on, is regression a good idea? Should we be doing it? And one of the best things we have right here for this is going to be check regression. Check regression. And here we are. And the answer is there's only one problem with this regression. And the one problem with this regression is the normality of the residuals seen over here in the QQ plot, the normal quantile plot. And it's kind of seen in the histogram too, but we don't like to look at histograms. Now, this is confusing for a lot of people when we do the check regression because they say, aren't high p-values good? A high p-value means you do not reject the null hypothesis. So we have to know what the null hypothesis is. And the null hypothesis is linearity is good, equal spread is good, normality is good. So if you do not reject the null, you would not reject that linearity is good. So you believe linearity is good then. You're like, well, I mean, I don't reject it. Linearity seems to be good. And that means the linear model is appropriate throughout here, that the line is going through the data well. You could have issues. Here, I'll pull up another data set where we do reject linearity. So let me go to data survey 10, where you can see a problem with the linearity. And we're going to make a separate model here with the height is what we're predicting, the height of an individual, and the weight, and survey 10 data. These are the variables inside. And height not found. Oh, is it capital? It is, right? There we go. And now when you visualize the model here, you can see at the end especially, there's this drift where the model's not going through the center of the data. And now we go right here and we take a look at the check regression, and you can see it actually fails all the conditions. You can see this is your line. The line has been flattened on the residual plot. We talk about that a lot in 201, how make a residual plot, you make the line flat. But you can also see the bend at the end where the points are not going through the line right there. The points are not scattered around the line. So a lot of major problems right there with the line. Also over here, we see problems with the normality of the residuals. And also there's apparently a problem with equal spread of the points, which it looks to get tighter. It's just kind of weird. There's not equal spread though. So we got problems with everything with this regression. And that's because the low p-values have us reject it. And I would say there's probably a good problem with normality of residuals, also linearity at the end of the model, and maybe some equal spread and outliers. So this is the check regression, and it's going to let us check our regression to see if there's issues. The three issues we are looking for again is there a problem with linearity? QQ straight enough. So that's one of the problems in Stat 201 we encounter. The next problem is equal spread or plot doesn't thicken. So this one has a problem of plot thickening, where the first one does not, even though you say like, well, isn't that getting thicker over there? Nah, it's probably just an outlier. Because when we check regression, the equal spread comes back fine. Even though you're looking at this and saying, well, wait a minute, that's spreading out more in the center. We don't have enough evidence yet to say there's a problem here. So we would not say for this regression that there's a problem with linearity or with equal spread. It does do 2 p-values for the linearity. Right now, these p-values are the same because the x variable is the overall model. When we get into multiple regression, we'll have to look at multiple p-values. The normality is the only problem over here, and you can really see it in the normal quantile plot. And once again, we have a problem because the p-value is low, meaning we reject the null to say there's evidence of a problem with normality of residuals. And once again, we see it over here. So there's a good bit of a problem with that. This is the check regression, and it's used to check our regression to see if regression is appropriate. And it looks like we may have small problems here, but on the other one, I would say we have much larger problems. We have all 3 problems to some extent. Problems with linearity, especially at the end where the points are not evenly scattered around the line. Problems with equal spread, where it looks like towards the end they get a little bit tighter. Look at how the points here have less spread, and over here they have more spread. I'm not as concerned about this one. I am also more concerned about the normality of residuals, where we have some points that are way too low, especially down here, over here, and these show up over here in the plot. Histogram, not a big fan of. More a fan of the QQ plot for normality of residuals, where we can see it does not follow what the normal says we should see. The red line is what is expected given as normal, and then our points are way too low. They are way lower than the expected, and that's seen down here in the plot, that the residuals for these are way lower than we would expect given they are normally distributed, i.e. we reject that they are normally distributed, and we have evidence they are not normally distributed, and that's an assumption we do not want to fail. So with this right here, I would say this regression right here, height and weight, has major problems. I'd be wary about using it, and I don't know if we really can interpret the quantities here on the screen because they might not be reliable, and that's something we'd want to communicate to people. So what else could go on with this? Well, let's look at this in influence plot. An influence plot tells us if we have influential points in the model. So influential points are points that pull the model in a direction. So when we have points that are pushing or pulling the model towards a direction, they're called influential. And you have to have 2 things to be influential on the model. To be influential on a model, you need leverage and you need a deleted studentized residual. So what is leverage? Leverage is probably the more complicated one, because to have leverage, you have to be far away from the mean of the x's. Now, we only have one x variable here. So a point with low leverage, I think the mean is about here. A point with low leverage, really? This is going to crash. A point with low leverage would be at the mean of weight. We'll give it a moment. Restart the program. Okay, there we go. So this is no leverage. Hey, what's up, Shinna, right there? And then the further away you are on this teeter-totter, you have more leverage. Now, what's confusing for people is when you look at this right here, that point at the fulcrum of it is going to be where things have 0 leverage. So when you look at a leverage plot right here, that no leverage spot is down here at the bottom. Where things start to have a little bit of leverage or too much leverage might be here, and that's where this line is at. It's kind of an equidistance away. The amount of leverage is a calculation we do in the background, so it's not relative to the numbers on the bottom. It is relative to a distance you are away from the mean of the x's. So this line right here would be corresponding to the yellow line, where the blue line is 0 leverage, because those things are on the mean of the x. And I wish I'd drawn it better right through the fulcrum right there. There we go. Mean of the fulcrum. I can't do it. There we go. So this means no leverage on the mean of the x's. This means high leverage. And this point over here, if you look at like this point right here, that's one of the points with the most leverage. But watch out, a point down here, like this point way above, is probably going to be that point right there because it has a lot of leverage. It's beyond the point of leverage, but it's just on the low side. Leverage doesn't care about positive or negative distance from the x or from the mean of the x's. Leverage is just how far are you away? How much push or pull do you have on this teeter-totter? So to have zero leverage, you'd be at the mean of the x's, but to have undue leverage, you'd be a far distance away. So that's what we need to look at when we think about leverage. The other concept, deleted studentized residual, is a little bit easier to understand because all we're basically looking at here is a residual. So if you were to take this right here and correspond it over to the other plot, the points with large deleted studentized residuals, makes it a little bit smaller right here. Large deleted studentized residuals are going to be points like down here, these clusters of 2 down here. Those clusters of 2 are down here. Notice how they're below the line. The line would be here. That's where the red line is. And then there's a point way above, and that point way above is this point back here. Remember, this is just far away from the mean of the x's, and that's why it has high leverage, but it's the point that's really far above. You see how it's most above the line, so it's kind of easy to trace over here and say, this point right here is the one that's most above the line, so it's that point over there. This point could be this point right here. Kind of hard to tell at that point because it's clustered near all these other points, which are kind of in this sort of realm of something of there. But the one point I want to point out again is the point with the highest residual is this one right here. It's the most above the line, and it's over here. But what does the idea of deleted mean? Well, the idea of a deleted residual is if you have a model. So here are our points. And then we have a point over here. That point is going to pull the model towards it. But without it, the model might be like this. So imagine we have data and the data goes like this, but then there's a point pulling the model up. So its residual would be that distance. But if you delete it as if it didn't exist, then we'd have the black line right there, and its residual would be this. So a deleted residual removes the influence of the point and creates a line without that point's influence. So we call it a deleted residual. So to make a deleted residual, you remove the point's influence and redraw the line. So we just delete the point, and then we say, okay, what would the line be without the point pulling it towards it? And then let's calculate its residual. And that is the deleted residual. Studentized sounds a little bit crazy here, but studentized relates to the student t, which is pretty much a z-score. And the idea of studentizing it is to standardize it. And as we've learned in Stat 201, we have the 68, 95, 99.7 rule using the normal curve. So when we think about things that are unusual, it still applies to the idea of t-scores that things outside of -2 and 2 would only occur generally less than 5% of the time. And that's about, these are all rounded percentages here, but the idea of 68, 95, 99.7 still applies here. And we would say that something is unusual when it's outside of 2 or -2. And that's why we put these bounds on here to say this is unusually high, this is unusually low, and a lot of things will be towards 0, which means they were right on the line. So remember, zero residual means right on the line. These are very low, and that's extremely low. It's a standardized distance of about -6. This is a standardized distance of about -5. This one's about -5 also, but it doesn't have enough leverage to be influential. That might be that point right there, it looks like. It looks like that point is very low residual, but it's right there on where the high leverage would start. So a point to be influential must have both these qualifications. It must have high leverage, which means it's far enough away from the mean of the x's. It must also have a high deleted studentized residual, which means it's very far above the line or very far below the line. And take into account the idea of deleted studentized, meaning we've standardized it to a metric that we can talk about -2 and 2 as a standard. And also deleted means we've removed its influence, so that way it doesn't kind of pull the line towards it. So we now know that we're looking for things in the following 2 regions. We're looking for things in this region That would be a high deleted studentized residual with large leverage, or a low deleted studentized residual with high leverage. And that's why we put these X's right here. And you can see there's a few of them. The size of the circle is the size of the influence. And there are a few points that have kind of high influence but didn't meet the criteria. So you could probably, if you want, look at that point right there too. But these are the row numbers of the things with high influence right here. And let's go ahead and store this as output. And when you get your output right here, you can get the leverage rows and go to your data set. We're working with survey 10 right here. And there's the rows. So we might only want to look at things that we're considering here, like height and weight. And if you take a look, that person is 4'6", 260 pounds. The other person is 5'7", 250 pounds. The other person is 6'3" and 75 pounds. So you got a lot of people here that are very heavy, very short, or very short, very heavy. So very odd combinations of what we have going on. So really odd. Chapter 8 quiz, I'm curious, can you walk through? Yeah, which ones? Yeah. Feel free to ask Sheena. I was just going over some output right here that we can have and go over. But yeah, this is some of the output we can do, and yeah. Try to think what else this week. We might tell me which question to do. Let's see. Ooh, someone's got some good stuff right here, and then we'll do the next stat to one question. We're going to get ads for tacos. Accompanying plot and regression only. The question about the accompanying. Yeah, who was the next? What I got? Random faces. That's not beautiful. We'll find something better later today, but they've got their fitted model right there and the residuals. Can we just run this on the model? Might make something decent. So we've already got our model stored into M. Well, there you go. There is the ggplot of that. Hey, Sam, what's up? I'm going to do another stat to one coming up here. We store graphics into P. And let's go here to Plotly. And, oh, it doesn't like it. That's interesting. What does it not like about that? Oh, just a warning message. That's fine. Warning messages are okay. But there we go. There's the points, and we can see the residuals now and the fitted model. I feel like we could do better, but yeah, trying to think what else there is. But quick code right here just gets us our model, our aesthetic, our labs, our horizontal line, all that stuff right there. So let's go check out this next question. Here we go. Okay, the question about the accompanying plots. Former student here, I now work at Al and DS to test the capabilities of GPT-3. Oh, yeah. I tried to do my old homework from classes. It did it perfectly? Oh, cool. Which ones? Which ones? Cola Coca. Interesting name right there. AI and DS. And you work in artificial intelligence and DS data science? Data science, right? Artificial intelligence and data science. That's awesome. Which assignments? And we're going to have people doing that. So thank you for being here, Coca-Cola or Coca. Which assignments? That's something we are very interested in. I've had a lot of conversations how ChatGPT and everything is going to shape education, how what we're doing. Yeah, but I've actually changed up the assignments this semester. I did right for all the ChatGPT and everything. All of a sudden, everyone was like, ChatGPT. I had to train a model based on some answer sheets to get the right type of output. Nice. So you're training models? That is awesome. Was it BAS 474? You had to do all those assignments? Email me at like bstevens@utk.edu. Homework exams, all of it. What? Yeah. I mean, this is crazy, right? Pretty interesting what it's capable of. And yeah, like they're saying it can pass the bar. Really interesting. So what we've been talking about is we probably want students to use it to do assignments and then to be able to fix and understand and make things better. Okay, but use it to teach people better methods, not penalize them though. Exactly. Like use this and then get better at what it does. That's awesome. Thank you so much for swinging by and saying all this right here. That's very important for us to know. The question about the accompanying plot and regression output. The accompanying plot. Finding a question in the background. Yeah, definitely. One more song. Here we go. The accompanying plot and regression output. Let's go check it out. Step to 1, shop the 8 quiz. Okay, let's check it out. The accompanying plot and regression output show the federal rate on 3-month treasury bills from 1950 to 1980, and the regression model fit the relationship in rate in percent in years since 1950. So this is where you have to be very careful with this problem, is they are going to then put it into years since 1950 right here. Well, they just give you all the data right there. Little bit of heteroscedasticity right there, so it's getting a little more spread out, plot thickening. Mostly good, mostly linear, so good with the conditions. We have an R squared of 77.6%, which is 77.6% of the rate is explained since 1950. They're calling the S rate here probably the residual standard error or residual root mean square error. We don't usually talk about that into a 1, but that's the typical miss the model makes, like on average how far are things away, about 1.2 in percent. The intercept is at year 1950, we would predict this interest rate. And then for each additional year since 1950, we would predict that the interest rate is increasing by this amount. That is the coefficient of the slope right there. Okay. What is the correlation? When we look at correlation right here, correlation can be negative or positive, so we have to look at the line itself. We also know that correlation is R, and we have here R squared. So if we take R squared and we square root it, we get correlation. So there we go with that. And there's the correlation rounded to 2 decimal places. Interpret the slope and the intercept. On average, interest rates during this period were increasing at about, and they want the slope right here. So the slope is 0.25. Is it 0.25? 0.25. And it started off at 0.61 right there. That's the intercept. So very important to know in the output, we have here the slope and the intercept right there. What does the model predict for 2042? We have to figure out how many years that is since 1950. So it's 92 years, but 2042 minus 1950, it's 92 years. Now we have to plug it into the equation. To plug it into the equation, let's write the equation to begin with. So here we're given the values of the slope and the intercept. We'll zoom in on this a little bit right here. So let's take the slope and intercept and write this out. So we have here the predicted y value, which I think we're predicting interest rate. So we'll write here int for interest predicted is equal to the intercept of 0.610. That's a 6 right there. You can't tell by my handwriting though. 0.61085 plus 0.24789 times the years since 1950. So years since 1950. And we're just going to plug into here that 92 we found a moment ago. So all we're doing is plugging into it, and I've went off the screen slightly. Bring that back over here. We're going to plug in the 92 into the equation. And when we plug in 92 right here, let's go ahead and do that. 92 gets plugged in. 92 times 0.24789 plus 0.61085. There it is right there. Okay. There's the interest rate rounded to 2 decimals. Boom. Would you expect this to be accurate? This is a huge extrapolation of the model. If you look, the model only goes to 1980 because the model right here is 30 years past 1950. So it only goes to 1980. This is a crazy extrapolation. So all we're looking for is extrapolation right here. Yes, extrapolation is close enough. No, we can maybe predict 1 or 2 years in the future. Extrapolation is a matter of degree, as in you could maybe get a good idea what's going to go on over here, but we're way off the model. We're out here in space. So this would be a huge extrapolation of the model. So I would not expect the model to make accurate predictions right there. Really good problem. Knowing extrapolation is when you make predictions outside the X bounds of your model is very important right there. So make sure you understand what's going on with the model. There we go. Any other questions right now? We did a little 320. We did some 201. We got a lot of chapter 12 done today. So really good stuff on chapter 12. We'll see if there's any other questions right here. But what else are people wondering about? Let's see, has Discord asked anything? Do we move the admin channel down? Did I do that? I'll do that. Maybe I did. Well, might end a little bit early here today, but we've done a lot of good work today. An hour and 26 minutes in. Got a lot of chapter 12 done today. Got a lot of chapter 8 done yesterday. But swing by here anytime. Swing by, ask questions, email questions, what you got. I might do some more emails here, reply to people. But let me know what you're working on. Let me know what you're thinking of, and we can get the work done. Till then, bye for now, everyone. Bye.